You know, when we picture how a plane flies, we usually think about air flowing smoothly over the wings, right? But what if I told you the real secret to lift isn't about how air flows forward, but how it spins? Yeah, to really get it, we've got to go beyond simple velocity and dive into the wild world of vortices. Okay, so let's start with something we've all probably seen, streamlines. You know, they're the classic diagram in every textbook showing the path air particles take as they flow over a wing. They give us this beautiful map of the velocity field, basically where the air's going and how fast it's moving. This is pretty much Aerodynamics 101. But here's the thing. Streamlines only tell part of the story. They show us the linear motion where the air is going, but they tell us absolutely nothing about its local rotation. So how in the world do we actually see the spin? How do we visualize all that air tumbling and turning on itself? Well, the answer lies in this amazing concept called vorticity. Vorticity, that's the Greek letter zeta you see there, is basically the tool physicists use to measure the local spin of a tiny little chunk of fluid. Imagine sticking a tiny paddle wheel in the flow. If that wheel starts spinning, bingo, you've got vorticity. Mathematically, we define it as the curl of the velocity vector. Now, don't let the math scare you. You can just think of curl as a way to measure how much a flow field would make a small object rotate, right at that specific point. It's our mathematical handle for quantifying that spin. Okay, so this leads to a really cool and powerful idea. I mean, if we have streamlines to visualize velocity, shouldn't there be an equivalent tool for visualizing vorticity? It just makes sense, right? We need a way to connect all those dots of spinning fluid. And here it is. It's this beautiful, perfect parallel in the math. We know streamlines are lines that always run parallel to the local velocity vector, q. Well, check this out. In the exact same way, we can define vortex lines as lines that are always parallel to the local vorticity vector, zeta. It's the perfect analogy, but for spin instead of forward motion. And we can actually take this whole idea one step further. You know how a bundle of streamlines makes a stream tube? Well, a bundle of these new vortex lines forms a vortex tube. Think of it like a self-contained tunnel of spinning fluid, flowing right through the main body of air. So that's great, but how do we measure just how intense that spin is inside the tube? For that, we use a quantity called circulation, which we represent with the Greek letter gamma. It's basically a measure of the total rotational strength of that whole vortex tube. And here's the really crucial part. For an ideal fluid, this strength, this gamma, is constant along the entire length of the tube. It doesn't get weaker or stronger as it goes. Okay, now in the real world, trying to model and track an entire tube of fluid is, well, it's super complex. So what do engineers do? We simplify it. We imagine shrinking that vortex tube down until it's an infinitely thin line, and we call that a vortex filament. It's basically a line of pure, concentrated vorticity with a specific strength, gamma. And let me tell you, it is an incredibly powerful tool for calculating the forces on wings. So, how do these vortex filaments and tubes actually behave? They're not just random. They follow a really strict set of rules. These were laid out way back in the 19th century by Hermann von Helmholtz. You can think of them as the fundamental laws of physics for how vortices work in an ideal fluid. All right, here are the three big theorems. First, like we just said, the strength of a vortex is constant all along its length. Second, and this one is a huge deal, a vortex filament can't just start or stop in the middle of the air. It has to form a closed loop, like a smoke ring, or it has to stretch all the way to the boundaries of the fluid. And third, a vortex moves with the fluid. The very same particles of air that start spinning together, they stay spinning together as they travel along. A vortex can't just vanish into thin air. Okay, that second rule should really make you stop and think for a second. If a vortex can't just end, what happens at the tip of an aircraft wing? Does the vortex that the wing creates just stop there? According to Helmholtz, no way. It can't. And right there, answering that question about the wingtip, that's the key. That seemingly abstract rule from Helmholtz, it's the crucial link, the absolute missing piece that connects this whole theory of vortices to the very real, very practical force of lift. And hey, this isn't just some vague idea. The Kata-Joukowski theorem gives us the hard mathematics to back it up. It basically states that the circulation around a wing is directly proportional to the lift it generates. It's that simple. More circulation equals more lift. That's a fundamental law of aerodynamics. So here's how it all comes together. As a wing slices through the air, its shape and angle create circulation. We model this as what's called a bound vortex that's kind of attached to the wing. But here's where the magic happens. Remember Helmholtz's rule? That vortex can't just stop at the wingtips. It has to go somewhere. So it peels off the wing and trails behind, forming those famous wingtip vortices you can sometimes see on a humid day. And it's the strength of that circulation, the part that's bound to the wing, that directly creates the upward force of lift. So this is what it looks like in an ideal world. The streamlines of a perfect vortex are just perfect circles. Now, when you take the circular spinning motion and you combine it with the forward motion of the airplane, that's what gives you the pressure difference that generates lift. This spin, it's the fundamental engine of flight. To put it as simply as I possibly can, just look at this chart. As you increase the circulation, gamma, around the wing, maybe by pitching the nose up a bit, the lift goes up right along with it. It's a clean, direct, proportional relationship. More spin, more lift. So the big takeaway here is this. Lift and vortices are basically two sides of the same coin. You really can't have one without the other. To truly deeply understand the physics of flight, you first have to understand the physics of these invisible, spinning tubes of air. They are completely inseparable. But this leaves us with a really fascinating paradox, doesn't it? If this circulation, this vortex, is the very source of lift, then why do engineers put winglets on planes and work so hard to minimize those wingtip vortices? I mean, if vortices are what make us fly, why on earth would we try to get rid of them? Well, that's a story for another time.